Hi, everyone. Thank you for joining. And I am here to talk about how to build a management layer over your data lake for structured and unstructured data. Just to introduce myself a bit, I'm a former, what now would be called data scientist, what used to be called an algorithms developer. I actually come from the realm of graphs rather than statistics or anything else. But I developed algorithms in the industry and later on turned to the dark side and started managing R&D organizations, the last of which was at SimilarWeb. For those of you who are unfamiliar, it is an Israeli startup company that IPO'd in 2021 and has tons of data. This is a data product with a lot of data, and that is where I first encountered the use of Hadoop and Spark and went through the evolution of the data tools from 2014 to about 4 years ago, which is where, after my experience at SimilarWeb, together with my co-founder, Oz Katz, started a company called Treeverse, which is behind the open source project lakeFS that provides scalable data version control, and we will mention it briefly today. And the reason we have this beautiful picture of a lake is because we're going to talk about data lakes, and because I am an open water swimmer and I love swimming in such beautiful lakes as this one. Last lake I've crossed was the lake in Geneva. 70 kilometers relay swimming. It was great. Okay, so let's start. What is our challenge? The challenge that we have is data lake manageability. To explain why that is a challenge, let's start by recapping what is a data lake, and when we adopted it, what have we lost and what will we be trying to gain back. So basically, a data lake is a utilization of an object store to the need of actually storing data for analysis. And then instead of having an organized database where we would need a schema and we would be putting the data in there, we would be just throwing in files into this object storage, and then we'd have a bunch of technologies that are able to read and analyze data directly from that object storage. So we are moving from a very organized environment of a database to a much scalable but less manageable environment of a data lake. What does it mean when we do that? What does it mean for us as data practitioners? So what do we gain? And we've done that a long time ago. I'm sure everyone here uses S3 to some extent to store data. So first of all, the write performance. When we don't have a schema that we need to adhere to, and we can just throw stuff into the storage, and the storage is built well, which object storages are, it is highly parallelized, and we can write a lot of data in parallel without thinking about the consequences. Consequences being what's going to happen when we have to read it. But that is an advantage in a world where the amounts of data that we manage constantly grow. As I said, no schema is required, so we can use any format of data that we see fit. And we don't even have to be consistent with that. We actually leave that problem to when we read the data. And that allows us a lot of freedom and performance when we write. Structured or unstructured, so it's suitable for all types of data, highly scalable and highly durable. So availability issues with even cloud-managed object storage are rare. They do happen, by the way, but they are rare. So I think 11 nines is the durability of S3, something really amazing. But we also lost a lot. If we used to work with a database, preferably one that provides OLAP, then we lost quite a few things that are extremely useful if we manage data, especially structured data. So when we use a database, the schema is enforced and it can evolve in a way that is safe. We have secondary indexes. So just to explain, object storages do allow a primary key, a primary index, and they're very efficient in, if the data is correctly organized in the object storage, they're very efficient in listing and hence in actually managing that specific index, but they do not have any secondary indexes that you can work with, which is the power of OLAP in a database. Databases provide ACID guarantees, so transactionality, atomicity, basically a lot of fail-safes that make sure that transactions end before others begin, solve concurrency problems. All those things, all those safeguards don't automatically exist when we manage data in an object storage. There's also the great ability of mutability. So if we already have a table in a database and we would like to delete a row, we can simply do that. We can append stuff, we can insert, we can update. All those capabilities exist, while object storages are immutable. If we want to change one row in a file, we would have to actually rewrite the entire file and to replace it. So we would now have the old version of the file and a new version of the file. Or if we don't want to save the old version, we simply replace the files. But that is a very heavy operation in relation to small or simple changes that we want to make. Databases for structured data have a standard interface. It's called SQL. I'm sure you're all using it. Accessing data in an object storage with SQL requires some work. We will talk about it in a minute. And of course, there is granular access control. A database is an application. It has access control. Object storages provide access control as well, but it is on the file or the partition level, while databases can provide much granular access control. So because I want this to be slightly interactive, if you don't mind, I'll stop here and ask if there are any questions or any comments that you would like to give, if you agree. Anyone? Okay, so I'll take the silence as an agreement and continue. Okay, so how do we gain this back? I mean, we love everything we gained, but we don't like pairing prices, right? So we want to gain back everything that we lost. We want to keep the advantages and minimize the disadvantages and get closer as possible to where we were. And happily, we have tools out there that actually allow us to do that, and even to do more than what we ever had with a database. So let's review them and see their role. So the first one is open table formats. I'm sure you have heard of Iceberg, Delta, and Hoodie. So open table formats are there to create an abstraction of a table in a world of files. So we talked about object storages being stores of files. Those files do have formats, such as Parquet, CSV, or whatever format you chose to use. But when you access the data directly in the storage, what you see is a list of files. We now want to be able to get actually an abstraction of a table. We want to be able to treat those files as tables and to gain some of what we have lost in the management of tables. And the way open table formats do that, and I'm trying to be as high level as possible, but still get the intuition of that, is they would allow us to save files in a certain format, Parquet, that holds the data in columns. It would also allow us to save deltas of changes. So let's say I want to now append additional data to a certain table, I would just save another file. If I want to insert something, I would save another file with what I wanted to insert. If I want to delete, I'll do the same thing. And then there would be a layer of files that are metadata files. Their names actually change between the different Opentable formats, but the high-level functionality remains the same. We would use that log file, as it is called in Delta Lake, to actually explain the files that we have in the storage. So if a file includes a few deletions that we want to do, the log file would tell us, this file holds deletion operations here, here, and here. So when we interpret that log file together with the data files, we get the information on what the table should look like. We can also control the schema in that way. If we added now a column, the log file would know that operation happened when it happened in one of the delta files that were added. And when we read the data, we can interpret the log file to know that there was a column that was added. So we're adding a layer of metadata that creates an abstraction of a table. Still, we are leaving a lot of work to a compute engine because, as I said, someone needs to read the log files, they need to interpret them, and then they need to take the actions on the data to actually create the latest version of the data that now exists due to all those changes that we have accumulated in the storage. Most Opentable formats started by having that compute being Spark. So you needed to run through Spark or use Spark in order to read those. And as time evolved, other compute engines provided support to the Opentable formats, but it means that they had created that logic of running and interpreting those log files. Again, those are not called log files in other Opentable formats, but the idea behind them remained the same. There is something in the chat. I'll see if it's a question. Oh, it's not for me. I'm sorry, I don't know when the recording would be available. Okay, so those are Opentable formats in high level. So what did we gain back by using Opentable formats? So first of all, we gained a schema and someone who is responsible for its evolution. Those log files know when something changed. And there is a lot of logic that you can add around enforcing that or evolving that automatically within the format. And we gained the most important thing. I think that was the initial intention of the Iceberg. I think they were first creators, the mutability. So at last, we can look at a table and we can behave as if we're in a database. We can add and remove, we can delete and append either columns or rows. So we have the full control we had in a database. Although what happens underneath is a manipulation in files, for the user who uses the format, we have gained back that capability. We also gained read performance. I did not talk about that, but there is a way to get secondary indexes with Opentable formats. I think that would be a too long talk to go into the technology that provides that. But it existed even in Hive. It's called bucketing in Hive. So those are Opentable formats. Any question about Opentable formats and how they help us and what we gain back by using them? All right, let's move forward. So we don't want to use Spark. Let's admit that. Let's all stand up and say, if I could live without using Spark even once, I would be very happy. So when Opentable formats were born, and they were born with the concept of you must use Spark, they have really limited the number of people who can actually use them. Of course, in parallel, we got managed Spark and a lot of capabilities that allowed more people to access Spark in a more comfortable way. But still, that is a limitation, especially when most of us are working on our own proprietary Python application, for example. And this is where we want to have the Opentable formats accessible to everyone with the standard interface of SQL. So we add another layer of abstraction, and that is the meta store. It is now called mostly catalog, but I don't want to have the confusion between regular catalogs that might not be metastores and a metastore. So I'm using the term metastore because that is really what Hive Metastore, as the first metastore ever, had provided the world, an abstraction of a table within Hadoop, and what metastores do today to allow accessibility for open table formats. So we said earlier, we need compute for someone to read the logic of the log files and to actually interpret them and provide us with a version of the table. This is what the metastore would do for us. It would do it by actually reading the log files and implementing that logic of a table into a database that provides us with an SQL interface. So we can now have a representation of an iceberg or a hoodie or a delta table within the metastore, the way it is actually explained within a database schema, right? A database is also manage data in storage and have an interpretation layer of a schema. This would be our interpretation layer for the open table formats that we have chose to use. And once we have a metastore, we have actually a general interface of SQL, and we can now work with hoodie, delta, or iceberg with an SQL interface through the metastore. So what have we gained back? So the SQL, as I've mentioned like 5 times since the moment I said metastore, but also better access control. The moment this is actually a database schema in a sense, where the storage is our database storage, then we can provide better access control through the metastore. So the 2 main functionalities would be the abstraction of a table, so it could be read by SQL, and the access control. But since it also sees all the tables that we have decided to manage in the open table format, it can provide some of the ACID guarantees that we have lost. So we can now implement transactionality, and Iceberg catalogs already have transactionality within them, multi-table transactionality. So we can actually create a transaction that works on several tables and make sure that it finishes before anyone else has access to the data that we have manipulated, right? So this gives us this atomicity that we really need and this safeguard of transactions that exist in databases. As I said, Iceberg already has that. Unity Catalog for Delta Lake is about to launch that. And honestly, I am not sure what happens with Glue, but I'm sure they're not far behind. This became a basic expectation for people who are moving into this instead of using an actual database. So those are the metadata catalogs. Any questions? Any comments?
Did you see the question in the chat?
Yes, please.
The question in the chat.
Yes. Yes, absolutely. And you're going to talk about both in a second. So the question is, if I consider the Databricks Unity and Snowflake Polaris that was just launched as metastores, the answer is definitely yes. They both include a metastore in them. Not necessarily the case for Alasian or other what was classical 10-year-old catalogs that are meant for discoverability of data in an organization. This is why I made the distinction, but definitely both Unity, Glue, and Iceberg Polaris include the capability of a metastore. So they would bring this abstraction of a table of, in the case of Polaris, an iceberg table, in the case of Unity, currently Delta, but probably in the future, the near future, also Iceberg. We will talk about that when we get to the examples. And thank you for the question. Anyone else would like to share something or to ask anything? Yeah. All right, let's continue. This last layer that is most innovative is the data version control layer. It's innovative in the sense that it doesn't try to imitate something we had in the past and we are now trying to gain back, but rather faces the fact that the way we work with data had completely changed in the last 15 years. And we can't continue just managing data the way we did before. So all the tools I've shown so far say, yay, we can create this almost database in huge scale because of those tools of Opentable formats and their meta stores. But this is not enough anymore because we need to work with data in the way that we work with code, in a sense that we need to experiment very quickly and very safely. We want to move data from different categories of data that we are defining. For example, we have the Databricks medallion model that says, yeah, we have the raw data, but then we have the bronze and the gold, and actually at the end, the platinum data, that is the data that our consumers should consume. So all that should be done very efficiently and without the need to copy data. And this is where data version control tools come into play and provide that additional capability that will allow us to adopt engineering best practices in data. So now that we have our structured data in open and semi-structured data in Opentable formats, and we have a meta store, we would like to have everything with version control. Let's see what it is and why it's useful. So over the object storage where we store the data, and we also have the Opentable formats abstraction within as files within the object storage, we put on an additional layer. This is the open source project that we have created called lakeFS. And that layer gives us two things. It gives us git-like operations over the data. So we can now define a repository of our data, all the tables that come into play in our analytics or in the model that we would like to build or in any other abstraction of the data. We would put all those data sources together in one repository. And from that point on, we can use git-like operations to manage the data. We would be able to open a branch in order to experiment in isolation. We will be able to commit our changes and then go back and forth with that commit. Remember, it's a repository. The commit would record changes of all the tables that we have, not one specific table. So we can move or travel in time on the status of that repository, not of a single table. And then we can, of course, merge changes that happened into different places into one outcome, just as we do in code. All those capabilities should remind you of the way you manage code and the freedom that you have to collaborate and to make mistakes because you are protected by a version control system. So you can now do all that in a data version control system. You run a new version of the pipeline, you run it on the side, on a branch. If there are issues, you revert. You can use hooks to test. The way you work becomes very easy and very compatible with the way you work with code. Basically, it also offers an API to the storage. So when you work with a data version control system, and of course, you can use all the tools that you use today to work with the data. And this is a very, very short list. Basically, everything you can think of is supported with Opentable, with data version control and specifically with lakeFS. The only change is that now you have to specify the version of the data that you're accessing. And that would make sense, right? We would want to say whether we are on the main that we recommend be the production branch of the data, or we are now accessing our experiment 1 branch, for example, or a specific commit ID from the history where we want to have data the way it was at that time. And so, of course, everything exists in a UI, in a CLI, so just like using Git for code. And it allows to run things locally as well. Okay. I'll pause for questions here before we're going to talk about what we gain, just so that since it's a new concept, I assume, to some of you, to make sure that the concept is clear. Is it intuitive to you to manage data the way you would manage code?
You have a few more questions in the chat.
Oh, thank you. What techniques would you suggest for writing streaming data? Is it correct to assume that the Iceberg is the most advanced open table format? I think it is. I think that Iceberg had remained open. It got adoption at the beginning from very large enterprises that really helped Netflix in developing it. And it came from the need to develop very large tables with very many columns, actually. And I think the fact that it got contributions from the beginning and that it was initiated as open source and remained open source until about two years ago, and I will explain, that time gave it the ability to actually represent the needs. And yes, I do believe that Iceberg is the most advanced. Delta Lake started from a different point, solving a slightly different problem, but they are overlapping completely now. And Delta Lake has the disadvantage that although there is a community behind it, the main contribution is Databricks. And by the way, with Iceberg as well, because 2 years ago, the creators of Iceberg started a company, and from that point on, I think it hurt the ability of Iceberg to evolve to where the market needs it, and it started to evolve to where the business needs of Tabular, the company that was established by the creators of Iceberg, had needed it to go. And that is a trade-off that always exists. And now that Databricks acquired Tabular, Databricks actually holds both Delta Lake and Iceberg. And it's very interesting to see how and in what way it would serve their business needs. But no one pays $1.2 billion without thinking it would help their business needs. So sorry, it was a very long answer because I am, of course, emotionally involved in the process. Short answer is yes. So thank you for saying yes. And it is very intuitive to manage data as code. What happens to the metadata level when you are experimenting with data like code and perhaps new versions of the table have been created since? That's a great question. It means that the data version control system should also support the metadata layer. So it should support the catalog so that the versions of the table are represented within the catalog, and you can access through SQL a specific version of the table, right? Just like you would do if you access directly the storage and interact directly with Iceberg or Woody or Delta, you would want that same experience when you access the data through the metastore, which means that the good data version control tool would be able to support the metastores. Wouldn't that greatly increase storage resources? Excellent question. The answer, surprisingly, is no, it decreases them. Because what happens when you don't have a data version control system? A lot of people are copying data around. If you want to work in isolation, you just copy things to your own bucket or to your own partition in a bucket, and you play with it, and then you clearly don't delete it, as happens in most organizations. The data lake becomes a swamp, and it definitely holds a lot of data no one needs, but no one's sure that you can actually delete the data. That is a very common problem. And when you have data version control, you actually control the versions that you need. You save only those versions, and you use a capability called garbage collection to make sure that you delete everything you don't need. So, right, anything that is not pointed by an active commit or an active branch, you probably don't need. Otherwise, there would have been something active pointing to it. So by first deleting the commits you don't need and then deleting the branches you don't use, you run GC and you clear the storage from everything that you don't need. And the versions that you do hold are the versions that your business needs require. So with a data version control system, the costs actually reduce between 20 to 50%, because some organizations just hold a full copy of their production as a development environment. With lakeFS, they don't need that. And with any other data, I'm trying to be objective. I'm not. I think lakeFS is simply the best tool out there. I realize I'm not objective. Okay, any other questions? Okay, most data changes, updates happen upstream and are pushed to the lake via ETL tools. In such scenarios, where exactly in the data versioning happening? If this is happening at the lake level, does that not slow the rate of the consumption? So no, because you simply, when you actually write new data, it is automatically tagged by lakeFS as a version. So the influence on performance is very small. It would be a few milliseconds. So you won't be, there is a trade-off, but it's very small. We have users writing huge amounts of data, managing petabytes and exabytes and billions of objects without interference due to the very small overhead of lakeFS. Does that answer the question? So the pipeline would simply be reading and writing through lakeFS. The overhead is very small, and everything you want versioned, a version creates when you commit, right? So whenever you want something versioned, it will be versioned. Okay, so what do we gain when we have a data version control system? So first of all, we have a repository level version control. We can now have consistency between all the data sources or data artifacts that we wanted, and they would move together in time as we wish with our commits. We can better control our storage, and it is deduplicated, because right now, instead of copying data, when someone wants to work in isolation, they open a branch. A branch is a metadata operation, and hence doesn't require copying anything on the storage. So the storage actually shrinks. You can easily create a dev test or staging environments for data pipelines. This is our main use cases, foot in the door. Anyone who starts using lakeFS first uses the option of opening a branch and running their experiments there, or creating their models there in safety and isolation. And then whatever they want to save, they actually merge back to the main branch. You can revert or roll back. You can do that either on the main branch or while you're working. So you did some experiment with the data, you don't like what you see, you can simply roll back or revert to the last stage before you did that experiment and continue and do another experiment. If you want to compare two experiments, you can run them in parallel on two different branches and then just diff and see what's changed between the two experiments. In machine learning, our users actually use or run hundreds of experiments in parallel and then compare the hyperparameters automatically to see which one is the best or closest to what they have hoped. You can use write, audit, publish, the write, audit, publish concept of, you write the data, but you can test it or audit it or verify it before you publish it to consumers. You can automate that by lakeFS hooks, just like there are GitHub actions. And of course, you have full data reproducibility. That is in very many industries actually a requirement to be able to introduce the data that created a certain model, even if it was 3 years ago. By working with a data version control system, you allow that automatically and effortlessly. So those are a few of the benefits that you have by using data version control systems. Yes, there is a merge operation. And if there is a conflict, then the merge just fails and tells you that there is a conflict. But merge is very important because then you can ingest, for example, for the question earlier about the ETLs, you can ingest the data to the lake on an ingest branch, write the automatic tests that validate the quality of the data, and put a hook that merges the data into your main for the consumers to use if the test had passed. If the test fails, the consumers are not exposed to the bad data, but you have it on your branch so you can actually debug the situation and understand where the problem is. Thank you for the nice. I got a nice for the merge. And that is very, very useful. And this is actually how data version control is used in production. It is used to create those workflows where every intermediate stage within a production ETL is constantly being tested and data is promoted only if the test passes. If the test fails, you get an alert and you have the data at the time of the failure to debug. All of us being data practitioners know how difficult it is to allocate the data at the time of the failure to understand where the problem is. So lakeFS helps with that by putting those stops in your process that provided the data at the time of the failure. Anything else I can tell you about lakeFS or data version control? Yeah. All right, so let's go into the examples. Oh, sorry. So I promised examples with environments such as AWS, Databricks, and Iceberg. Once upon a time when Databricks and Iceberg were two different things, like a week ago. So I will give those examples, but refer to the latest changes as well. So with the Databricks ecosystem, we have the Delta Lake format as the Opentable format. Again, it's not to say that Delta Lake is not a good product. It is just lagging behind the capabilities in Iceberg. And what you see near that is actually a representation of unstructured data. Databricks is an extremely powerful product, and it can manage also unstructured data and provide tools to work with unstructured data, naturally being the company behind Spark. Spark is a very general distributed engine that can also analyze unstructured data, right? It just distributes the work in a very efficient way. So we have that layer of formats where Delta Lake is currently the Opentable format for Databricks, but I'm assuming Iceberg would be joining this line very soon, probably in stages. Right now, there is a connector that allows you to read Iceberg, but you only write Delta tables. I assume in the next few months, we would see that change and Iceberg tables being managed in Databricks naturally. That would mean, of course, that Unity Catalog that we had a question about a few minutes ago would have to support Iceberg as well as Delta. And it has a capability called volumes that allow you to manage unstructured data as well, or at least the metadata of unstructured data, which is extremely useful with machine learning, right? You would like to have all the metadata associated with, for example, a picture if you're working on a model in Vision, so that you can select all the pictures with cats, something we all do every day. And of course, over that, there is the very strong compute engine provided by Databricks that is based on its internal version of Spark that is implemented in C++. So that would be a Databricks example. I see a question in the chat. How does data versioning support schema versions changes? So in two ways. Once it doesn't stand in your way, so you can change the version, but you can definitely use data version control with the validation, right? So just like we said, we ingest data and then we test it. One of the tests that you can put there would be a schema validation. And then if the test fails, it means that the schema had just changed. No one told you. That is indeed a common problem. You can know and you can accumulate the data with this changed schema on the branch while making sure to fix everything going downstream from the pipeline from there. So in the verification and validation capabilities, lakeFS helps with schema evolution. Please note that if you are using an Opentable format, which you don't always can, but if you do, then both formats, Delta and Iceberg, have schema validation capabilities within the format itself. So you can choose whether you want the schema to evolve, and then it would change automatically if a change came in, or if you want it validated, then you would be notified that the schema had changed and operations have failed. Here, lakeFS could definitely help because it might be too late. Please go ahead. Someone tried to speak. Can comparison be applied to the commit to reduce storage requirements? Yes, we have diff for everything, if that is the question. So our compression, yes, of course, we support compression. Yeah, sorry, dyslexic, reading very slowly. Okay, so this is the Databricks example. If there aren't any questions or comments on this, I will continue. Okay, the AWS ecosystem is huge. So I selected one specific case here, and I'll explain why, but I'll mention a bunch of other technologies. So when it comes to Opentable formats, AWS betted on Hoodie 5 years ago, realized that wasn't a smart choice, just because Hoodie is a great product, by the way, but its adoption isn't as great. And then together with Databricks, they started supporting Delta Lake, and because everyone was using Iceberg, they also support Iceberg. So as one would expect from a cloud provider, they now support everything and also support the idea of unstructured data. But it all happens right now in one catalog, AWS Glue. And here I can share compliments. So I'll just say it exists. It does provide metastore capabilities, and it is not as good as other metastores out there, but it does provide the services. It's very hard to get it to scale, even if you're willing to pay tons of money to AWS. And then the tool I chose as the compute is Amazon Athena. All AWS compute engines actually work with Glue, but you don't have to use Glue. So if you use EMR, you can also use any Iceberg catalog out there or Hive Metastore. But when it comes to Amazon Athena, that imitates a database or a closed compute engine, it only works with Glue. So the only way for you to see your Iceberg tables or to query them through Athena would be to register them within the Glue catalog. So other AWS tools are more open, and Athena is the one that is closed and really relies on the Glue catalog as its schema catalog. So the reason I chose that. Glue, by the way, has not only a metastore or a catalog. Glue is also a compute engine, Glue ETL, which is a good product. And it is more friendly to non-technical people than EMR, but not as open as EMR. Any questions or comments on the AWS example? Okay, so last but not least, the latest, and I love this one because it just happened, and it makes Snowflake something else than what it was, right? So Snowflake, as we know it, is a database. It's an amazing database. It's a database that actually split between its storage and its compute and gained a lot by doing that. It's a very strong compute engine and a very expensive one. But up until last week, you could query external tables through Snowflake, but the way you would think of Snowflake would be as a database, while the way you would think of Databricks, you could also think of Databricks as a database, but you could use the different components of what makes Databricks a database, while Snowflake came in one piece, right? So when they have released Polaris to the world last week, they said, okay, no, there is the internal database schema of Snowflake, but now we are adding another one, another catalog, not the internal catalog that we have, but rather another catalog that supports Iceberg tables, no matter where they are. You can register them. Of course, it has to be where the Snowflake engine can access the data. But other than that, it could be a separate bucket that you have Iceberg tables on, and you register those in the Polaris catalog, and then Snowflake would become a compute engine working over that catalog and allowing you to query your Iceberg tables for read and for write. And this is where Snowflake is trying to go into the domain of Databricks, while of course Databricks for ages is trying to go into the domain of Snowflake and provide something that is similar as possible to an analytics database. So this is very exciting. It's very new. The Polaris is actually not open source yet, but they've promised to open it in 3 weeks from the announcement. And it's very interesting to see how good their catalog would be and how useful would that system become, and if it really would be adopted by people who only considered Databricks until now. All right, so closing words is just saying that if data version control is a concept that is new to you, lakeFS exists for 4 years. It is very widely used. It is extremely scalable, and it works very well in all those companies that you are seeing here. The logos that are larger are because they're really cool companies, but also because they are design partners of lakeFS and worked with us on improving this product. So you can try it out and add it to the architecture of your choice for making your data lake manageable. Thank you for listening, and I am happy to take any additional questions.
Thank you, Einat. It was great having you here. See you next time.
Thank you all, and goodbye.